Good afternoon. Just picking up where we have been working with polynomial inequalities, and I had given like a set of problems to be looking at centered around this trinomial where we have x squared minus 4x plus 4 is to be worked with, and we have as a quadratic equation. Okay, so we have this trinomial set equal to 0, and now for what we have here with x squared minus 4x plus 4 is equal to 0. Okay, if you were to factor, we would end up with the very same binomial expression times itself. In this case, the binomial we have x minus 2. And for what we're going to have in this particular case, right, we're going to have just 1 0 for the trinomial. Okay, so there's going to be one value of x, and from x minus 2 setting equal to 0, okay, we have that x is equal to 2. Now, in the case of what we have with the comparison to 0 inequalities, okay, so we have at the start, okay, so we have with f of x equal again to x squared minus 4x plus 4. Again, we have only 1 0, and that is with x equal to 2. And if we set up a table of intervals, okay, and we have, again, revolved about x equal to 0, we'll make that x equal to 2, which is our 0. Okay, so we have okay, so we have for the values of x outside of 2, you have those values of x less than 2, as well as those values of x which will be greater than 2. And we'll be, again, comparing this function to 0. Okay, less than, greater than, less than or equal to, as well as greater than or equal to. And, all right, so in establishing a table, okay, and again, we have two distinct intervals, and only two intervals, since we had only 1 0 in this case, which we had to be with 2. And looking at what we have, okay, again, just looking at inserting test values. Okay. All right, so for the test value x, okay, we can select anything that is less than 2, and we can just go with the number 0, let's say. And then anything greater than 2, okay, we'll just go with, say, the number 3. All right. And looking at what we have concerning the value of the function, in the function we have f of x equal to x squared minus 4x plus 4 and for what we have with our sample inputs, okay, with 0 and 3. Okay, so for f of x, if we have x to be 0, again, so we're going to have f of 0. Okay, so again, we have 0 squared minus 4 times 0 plus 4. And we have for the outcome, okay, this is going to be a positive 4. And for the input value at 3, okay, so x squared we have at 3 squared We have minus 4 times 3, followed by the additional 4. And again, so we got 3 squared is 9. Negative 4 times 3 is negative 12. And again, have followed by the plus 4 at the end. So 9 minus 12 is negative 3. And adding 4, okay, so we have a plus 1. And now looking at the sign values for f of x. Okay, so for values of x less than 2, okay, we'll have a positive output. Okay, so we have that f of x is greater than 0. Also for values of x greater than 2, the output is also positive. And again, we're going to end up landing, once again, the f of x is greater than 0. So just looking at what we have in terms of the inequalities that we have in setting up in comparison to 0. Okay, first of all, okay, if we've got in our scenarios, okay, so you have x squared minus 4x plus 4 is less than 0. Okay, now again we have our function f of x at x squared minus 4x plus 4, and this would be in line with f of x is less than 0. But if you notice in the table, okay, we have f of x greater than 0 for values of x less than 2. Also f of x is greater than 0, okay, for values of x greater than 2. And that's what we have for the solution. Okay, for the solution, okay, you can say that in this case, since we don't have any interval where the value of the function is less than 0, we say that for the solution, okay, there is none, or we could say D and E for does not exist. Now for x squared minus 4x plus 4 is less than or equal to 0. Now this would be in line with f of x is less than or equal to 0. And now for what we have in the case of the solution, okay, all right, now there's no value of x that would set the trinomial less than 0. But in the case of less than or equal to 0, okay, there's nothing from the less than 0 part, but we do have for the equal to 0 part. And again, we have going back to what we had when we were looking at the quadratic equation where x squared minus 4x plus 4 is equal to 0, and we had the x was equal to 2. So with the equal to 0 part, there is one value. Okay, so that's going to be x is equal to 2. So that would be the standalone value that we have here. Now, in changing the direction, for x squared minus 4x plus 4 is greater than 0, we now have where f of x is greater than 0. And from the results, okay, from the column settings, okay, we have f of x unanimously in the direction of greater than 0. And this will apply to both interval sections established. Okay, so we have for those values of x less than 2, along with those values of x that will be greater than 2. And for the remaining possible relationship of this function in comparison to 0 is where we have it to be greater than or equal to 0. Okay. So we have that f of x is greater than or equal to 0. And now looking at what we have here. So this will be going in the same direction as f of x is greater than 0. Okay. And there's going to be a bit of an added twist here. All right. So we got initially, okay, so we got between negative infinity and negative 2, made that negative infinity and 2, as well as 2 and infinity. Okay, now for this set, infinities are boundless, and since we now have equal to 0 included, and since we have that 2 creates a situation where we have f of x is equal to 0. We're going to start out with 2 that is going to be bracketed. Okay. And now what's going to happen here is that since we have 2 to be included, and it's going to be like a tie that binds these, what were originally these 2 separate intervals. So we can say that in essence, okay, the x is equal to 2 with it bracketed. We say that x equals 2 is going to unite the sections. And so for what we will have for the solution, okay, notice with this, okay, we have the entire real number system except for 2. You have those values less than 2, those values greater than 2. But now that we have 2 included, okay, we have 2 is going to be that piece that bridges the gap. And guess what? For this last case scenario, okay, we'll have the solution to end up as the whole set of real numbers. And that would be the final situation. All right. And now, for what we have in the case of the exercises on page 332, and we'll be looking into just the first of these. Okay, for I think this at least does provide a bit of semblance of continuity. And in the case of number 17, okay, now we're looking at the function, okay, where we have f of x is equal to negative x squared plus x plus 12. And we have in the first case, now we have with part A, okay, we're looking at where negative x squared plus x plus 12 is equal to 0. And what I want to do, okay, say that I want to make this as factor friendly as possible. So I can just not changing the resulting values of x. I don't want to do that. But I can multiply the equation by -1 or divide by -1. Just, in essence, just change the signs of the terms we have in the trinomial. And you can multiply or divide. So just in the rewrite, I'm going to have x squared minus x minus 12 is equal to 0. And so with the reformatting, I have a trinomial that I can factor into binomial expressions with x as the first term. And we have with factors of -12, whose sum will be -1. We have more weight given to the subtraction than the addition. Okay, so we got x minus 4 times x plus 3 is equal to 0. And looking at the zero product property, if I set x minus 4 equal to 0, we're going to have that x is equal to 4. And for x plus 3 is equal to 0, I will have that x is equal to -3. So we're going to have a couple of solutions here. One positive, the other negative. Okay, so you got 4 and -3. And just setting things up, okay, in terms of solving inequalities. Again, so I have f of x is equal to -x squared plus x plus 12. Okay. And again, just from part A, okay, we got with the zeros of f of x again, so you have x equal to 4 as well as -3. And if you look at establishing, once again, a table with a top row, okay, consisting of intervals. Okay, all right, so proceeding from -infinity, okay, so we have approaching the smaller of the zeros, in this case, which will be -3. And bypassing -3, we have for the next interval, we have between -3 and 4. And then for the remaining possible values of x, here we have those that will be greater than 4. And looking at what we have, okay, just setting things up along the lines of taking samples. Okay, so we have for a test value x for each of these interval sections. Okay, so for anything that is less than -3, okay, we go something like -4, -5, or say -5. And then we have between -3 and 4, we'll just go with 0. And then we have anything that is greater than 4, we'll just go with 5. Okay. And again, we're looking at this function, f of x. Okay, so we have -x squared plus x plus 12. All right. So for what we have in the case of f of -5, okay, plugging in, okay, this is where you had to be careful with the sign values. Okay, so we got the negative, opposite sign of -5 squared plus -5 plus 12. Okay, Now, square of negative 5 is a positive 25, but again, I'm taking the opposite sign of this. So this is going to become negative 25. And we've got subtracting 5. Then we have adding 12. So we've got negative 25 minus 5 is negative 30. Negative 30 plus 12. Okay, this will come out to negative 18. For what we have in the case of f of 0. Okay, so we got minus 0 squared, so that will be negligible, plus 0 still negligible. And we have the addition of 12, so we have for this output, okay, this will come out to plus 12. And for what we have in the case of f of 5, okay, so we've got the negative of 5 squared. And we have plus 5. And we have plus 12. All right, so 5 squared is 25, but again, I'm taking the opposite sign of this. And we've got negative 25 plus 5 is going to be negative 20. And in turn, negative 20 plus 12, okay, that is going to end up at negative 8. Okay, so upon testing out the intervals, after all the sampling that is done, okay, so right now, okay, so you had with the input value of negative 5, again, the output was negative 18. And for the input of 0, okay, the output was positive 12. And for the input of 5, okay, the output was negative 8. Okay, so for what we have in the case of the sign of the function, okay, whenever the input is a value that is less than negative 3, like taking negative 5 as the case, right, the output, okay, which in this example led to negative 18, okay, this signals that for all values x less than negative 3, okay, your output is going to be negative. So we have the f of x is less than 0. And then for those values of x such that negative 3 is less than x is less than 4, this time, okay, like 0 leading to positive 12, the output is positive. So we have the f of x is greater than 0. And for all inputs greater than 5, okay, the output will be negative. Okay, so the f of x is less than 0. Now where the inequalities come in for parts b through e. Okay, so we got for here we have negative x squared plus x plus 12. Okay, in the first case we have is less than 0. Okay, so this would be referring to where we have f of x to be less than 0. Okay, and so this is going to apply to the first and the last interval sections. So we have for the solution set, okay, so we're looking at those values of x less than -3, along with those values of x that will be greater than 4. Now, where we have that the expression is less than or equal to 0. Now, we got the same direction as in the case of f of x is less than 0. But with the equal sign, there is the potential for the existence of brackets. Not a guarantee, but there is that looming possibility. Okay, so we got for the limits, okay, we're still working around -infinity and -3, as well as 4 and infinity. And for the enclosures, now infinities are boundless, so those will stay in the parentheses. And since both -3 and 4 create the equal to 0 part, we thus have that -3 and 4 are included as solution values. So around these numbers will be brackets. And for what we have in terms of going in the other direction, so for -x squared plus x plus 12 is greater than 0, so you have the f of x is greater than 0, and that feature is going to be only in the middle interval section. So yeah, for the solution, it will be just those values x, whereupon we have -3 is less than x is less than 4. We got parentheses. Then we have for the remaining case, whereupon we have -x squared plus x plus 12 is greater than or equal to 0. Okay, so this is where we have f of x to be greater than or equal to 0. So you got the same direction as f of x is greater than 0. So we're still working around the limit values of -3 and 4. Again, thanks to the inclusion of the equal sign, okay, -3 and 4 are both zeros. And so they're going to be in the brackets. All right. And now, just sort of tying in inequalities in with the earlier topics we have had. And I had mentioned the other day that we will be looking at like where the y values might come in. And let's say that just going back to what we have been dealing with, like zeros, multiplicities, and behaviors, and all that. Let me give you a case of a function, and we'll put this in factored form. And let's say that if I were to determine the end behavior and we'll say for this function, okay, we'll say that we have f of x is equal to x squared times the quantity of x plus 2, and we have times the quantity of x minus 3. Okay. So looking at what we have for this function, Okay, so for the end behavior, okay, so again, we were looking at the sign value of the highest degree coefficient as well as the degree of the function itself. And so I'm going to copy this part here and looking at what we have for f of x. Okay, and just stressing the degrees. Okay, so you got, so you have x to the second, x plus 2, x minus 3, and just setting up what we have for the highest degree term. And we're not going to multiply all the factors throughout, but for the highest degree term, okay, what's going to have here? Now we got 3 factors. Okay, and for what we have, first of all, okay, so we have from the first factor, okay, we already have x squared. And then between x and 2, for this binomial expression, it is its own factor, and between the terms, x is of the higher order. And same thing with x minus 3. We have this binomial, x is going to be the higher order. Okay, and I'm not interested in all the terms, just what would be the highest order term if you're to multiply x squared, x plus 2, and x minus 3. So the highest degree term will come from the higher or the highest order terms from each of the factors. Okay, so we're looking at x squared times x times x. Okay, so I got x squared times x times x. So this will be x to the 4th. And I'll just stress the numerical value. So you have 1x to the 4th. And just looking at what we have for the characteristics and determining what the end behavior is going to be. Okay, so the leading coefficient a of n, they have equal to 1. When it's positive. Okay, and the highest degree term, well, that is going to be of degree 4, as indicated by x to the 4th. So n is equal to 4. And 4 is an even value. And so for the end behavior, okay. Again, just a reminder. Okay, so we have an even power, but if I had an odd power, like x to the 5th, x cubed, it's going to be up at one end, down at the other. But in the case of where we have even degrees, it could be either up both ways or down both ways. And since the coefficient is positive for the leading term, okay, we're going to have moving up both ways. Okay, so the end behavior is going to be up to the left, up to the right, or as Alex might have it, rises to the left, rises to the right. Okay. Now, I say that maintaining the use of this function. Let's say if I were to determine the zeros. If I determine the zeros, the multiplicities, and where the graph is going to cross and touch the x-axis. And again, so we have with this same function, okay, so we have x squared times quantity of x plus 2 times that of x minus 3. Okay, so with zeros and multiplicities, okay, so I'm just going to place emphasis on the degrees, but in a somewhat different capacity. Okay, so you have first factor, we have an x, and that is to the second, and outside the parentheses, you have x plus 2, not to any explicit power, so we have implicitly that we have x plus 2 to the first for x minus 3. Okay, that is going to be to the first. And just the backdrop here, so from the x factor, you have x equal to 0, and for x plus 2, if I set this equal to 0, I have the x is equal to negative 2, and for x minus 3, I have the x is equal to 3. Alright, so we have with the zeros, again just restate, okay, so from x, I have x equal to 0, from x plus 2, I have x equal to negative 2, and from x minus 3, I have the x is equal to 3. Now, in terms of the multiplicity of each, okay, so again, multiplicity would be the power to which each corresponding factor is going to be raised. So 0 stems from x, which is raised to the second. Negative 2 comes from x plus 2, which is raised to the first. Likewise with 3, this stems from x minus 3, which is raised to the first. And in terms of whether the graph crosses or touches the x-axis, okay, now again for odd valued multiplicities, okay, the graph is going to cross the x-axis, but if the multiplicity is of even value, then the graph is going to touch. Okay, so you have 0 has an even value multiplicity where we have the value to be at 2. So in this case, we have the graph to touch at x equal to 0. And with negative 2 and 3, okay, you have a multiplicity value of 1 when the power is odd, or the multiplicity is odd, the graph is going to cross. Okay, so we have crossing at x equal to negative 2. And also we have crossing at x equal to 3. Okay. And just looking at what we have, at least in the sort of the building blocks, and we're going to cross over to inequalities in reference to this very same function. Okay, just to be able to get a view for right now. Okay, so for this function, you have the end behavior, you have up to the left, up to the right, and we've got these 3 zeros, okay, which are going to be x-intercepts. We have touching at the origin and crossing at negative 2, 0, as well as 3, 0. And okay, so for what we have now, okay, so we got 3 distinct zeros. Okay, we have the origin, we have x equal to 0, and we have x equal to 3. And also we have x equal to negative 2. And for what we have in terms of the activity, okay, so again we have the end behavior, okay, up to the left and up to the right. Okay, and just for what we have in terms of the projecting, okay, so you have up to the left, so I'm going to project out from the leftmost 0, which we have at negative 2. And for what we have up to the right, I'm going to project from the rightmost 0, which in this case we have at x equal to 3. And for what we have in between, now if you were to read the graph in order from left to right, okay, so again, so at x equal to negative 2, now again the graph is going to cross, and once we get to x is equal to 0, okay, now the graph is going to touch, and once we get x is equal to 3, the graph is going to cross. Okay, and just filling in generally for what we have for the graph of this particular polynomial function. Okay, so if I go from left to right, okay, so I'm starting out left and above, okay, and if I go out to the right, so I'm looking at descending, and once we get to x is equal to negative 2, the graph is going to cross, and then it's going to go up, and it's going to arrive at the origin, and instead of crossing, it's going to essentially touch or bounce off the x-axis and go back below. And then it's going to start to go up again, and once we get to x is equal to 3, we have crossing over, where we have the graph to transition from below the x-axis to above. Okay. Now let's say that with our function, and say if we were to determine the let's call this the comparison to 0 inequality solutions. For what we have once again, okay, so we have for f of x, is equal to x squared times the quantity of x plus 2 times the quantity of x minus 3. All right, so for the comparison to 0, okay, so we got our function f of x. Okay, so we got x squared, x plus 2, and x minus 3. And again, just setting up the table. Now we already got baked in, okay, that the zeros of this polynomial are going to be 0, negative 2, and 3. And looking at setting up a table of intervals. Okay, we revolved about these zeros in working with this function. Okay, so we have out of 0, -2, and 3. Okay, so -2 is going to be the least of the zeros, or the leftmost, if you think in terms of a number line. So for at the lower end, we have those values of x that will be less than -2, and then we have bypassing -2, we have approaching the next smallest of 0 in this case, and that is going to be 0 itself. And then we have going past 0, and then we have approaching 3. And then for the rest of the values x, we have those that will be greater than 3. And looking at what we have for tested values. Okay. For those values of x less than -2, we can take, let's say, -3 as a sample. Between -2 and 0, if I want to work with integers, I can only choose -1. And between 0 and 3, I could choose, if I want to go with integers, I could choose either 1 or 2. And I'll just go with 1 in this case. And then for anything greater than 3, we can just go with the number 4. Okay. And again, for the function, again, f of x, we can have equal to x squared times the quantity of x plus 2 times the quantity of x minus 3 . So for what we have in the case of f of -3, and just plugging in, so we have the square of -3 times the quantity of -3 plus 2 times the quantity of -3 minus 3 . And square of -3. Okay, we have positive 9. -3 plus 2 is -1. -3 minus 3 is -6. And taking the product, okay, so we'll have a positive 54. For what we have in the case of f of -1, okay, so I have the square of -1, times the quantity of -1 plus 2 times that of -1 minus 3. And for what we have for the square of -1, that is positive. -1 plus 2 is a positive 1. -1 minus 3 is -4. And for what we have in multiplying, so we have the output is going to end up at -4. Now for f of 1, okay, so we've got 1 squared, times the quantity of 1 plus 2, times the quantity of 1 minus 3. So 1 squared is 1, 1 plus 2 is 3, 1 minus 3 is -2. And we have for the product, okay, so this will be -6. Now for f of 4, okay, so I have 4 squared times 4 plus 2 times quantity of 4 minus 3. So about 16 times 6 times 1. Okay, so that product, okay, that is going to be 96. And now looking at what we have with the sign values of f of x. I'm going to go ahead and just create partitions here. Okay, so we got our intervals, and we sampled with the various test values, and we've arrived at the various outputs. Okay. Okay, and for what we had in the case of the sine of f of x, let's see if I can change that up. Okay, so for the sine of f of x, okay, so we have when -3 is the input, now we have the output to be a positive. So f of x is greater than 0, and then for any value selected in x such that -2 is less than x is less than 0, the output is going to be negative. So you have f of x is less than 0, and then anything greater than 0 but less than 3, output again is going to be negative. So you have the f of x is less than 0, and then anything selected higher than 3, it's going to lead to an output that is positive. Okay, so we have that f of x is greater than 0. And just now looking at what we have here. And put in these partitions. There we go. All right. So we have with our function f of x equal to x squared times x plus 2 times x minus 3. Okay, we have the various cases, okay, in terms of how that function is going to compare to 0. All right. So we have, first of all, okay, so where we have x squared times the quantity of x plus 2 times the quantity of x minus 3 is less than 0. Okay. So we're looking at the same direction as where f of x is less than 0. And for what we have in the case of the solution set, okay, where we have f of x to be less than 0, again, the interval solution will have the exclusive use of parentheses as the grouping symbols. So we'll be looking at these two middle interval sections. Okay, so between -2 and 0, followed by those values of x that will be greater than 0 and less than 3. Now, for what we have in the case where we have the function to be less than or equal to 0. So we have along the lines of where we have f of x is less than or equal to 0. Same direction as where f of x is less than 0. And we're still looking at working around the same limits. Still working around -2 and 0. As well as 0 and 3. And for what we're going to have here, -2 is a 0, 0 sets it equal to 0. We have 3 also sets to 0. And just like from what we had in the special case from the first example, okay, we have notice you have between the intervals. Okay, you have the end of the first interval and the beginning of the second one is part of the solution, and so that is going to once again unite these separate interval sections. So the gap is going to be bridged. Okay, and so for the solution in this case, you're going to have running continuously from end to end between -2 and 3. Okay. And for the other direction, okay, we're not going to have that added special case to be applied because we're going to have the kind of too large a spread for there to be a tie that binds, so to speak. And where we have that the inequality is such that we have the function to be greater than 0. So we're looking at the first and the last interval sections where we have those values x less than -2 and those which are greater than 3. And for what we have in the remaining case, all right, where we have to be greater than or equal to 0. Okay, and all of 0, -2, and 3, where they can be applied. Okay, we have setting equal to 0. Okay, so again, infinities are boundless. -2 and 3, thanks to the equal sign, will now be parts of the solution, and so we're going to have those numbers again in the bracket. All right. And so for what we have in terms of the framework here, and again, just from the start, okay, we had the end behavior on the basis of the resulting highest degree term at x to the fourth, where the coefficient was positive and the degree is even. So the end behavior had up to the left, up to the right, and from the zeros and their multiplicities, again, you had at -2, 0, and 3 had cross, touch, and cross. And now for what we have in the case of seeing how this graph can sort of relate to what we have with the inequality setup table. Okay, and I'm just going to mention, okay, when we took samples here, like with x at -3, we have like a value less than -2, and we said that the output was positive. In this case, had +54. And this is like saying that if you were to graph this function, you would have like as a point, like whenever x is -3, y value is 54, and then with, say, any value between -2 and 0, like -1 being such an input, we had the output to be negative, in this case, -4. And then, say, selecting 1 to sample anything greater than 0 and less than 3, we ended up with negative output. In this case, we had -6. And then representing anything greater than 3, for the input we have 4, and the output was positive. In this case, we had 96. So in addition to these particular intercepts, okay, we have like these from these samples. They have like -354, also have -1, -4, again, I'm not drawing this according to scale by any stretch of the means. And then we have 1, -6. And also we have, at the extreme, we have 4, 96. And again, my graph might be way out of proportion, but in terms of the general behavior, this is kind of like what we have in this case. And so you have like your intercepts, you know, cross, touch, cross. You got the end behavior up to the left and up to the right. And again, so we have, and again, for the relative minima in this case, it might come before or after what we have for these points. I'm just kind of taking a guesstimate, so to speak. But anyway, I just want to give you like a view in terms of how the y values abound from using the table. All right, now there is one subcategory within the inequalities, and this is going to be for what we have in the case of rational expressions. And for what we have in the case of rational inequalities, and we'll say that we'll have as an example, okay, just kind of start out with, and in comparison to polynomial inequalities, you're still going to be looking at zeros, but you're also going to be stressing what zeros are in the domain as well as the zeros that are not. And let's say that if we have a function r of x is equal to x plus 4 all over x minus 3. Okay, and now we got a couple of x expressions, one in the numerator, the other in the denominator, and I'll just go ahead and identify those particular zeros. So like if I set x plus 4 equal to 0, we have the x is equal to -4 in the denominator. Okay, now the 0 from this, okay, we have x equal to 3. And 3 is going to be a restricted value. And so you got r of x. Okay, now for the zeros of r of x, okay, so for the zeros of r of x, I have x equal to -4. Okay, and again, if I have x equal to -4, I have -4 plus 4 is 0. Negative 4 minus 3 is negative 7. 0 divided by negative 7 is equal to 0. And I can have the 0 numerator as long as I have a 0 denominator. So x equals negative 4 is in the domain. And for what we have in the case of x is equal to 3, again, if you think of 3 plus 4 is 7, 3 minus 3 is 0, 7 divided by 0 is undefined. Okay. So again, 3 is not in the domain. Okay, and now, like the polynomial inequalities, set up intervals. Okay. And we have between negative 4 and 3. Negative 4 is the smaller, so we have for the first subinterval, we have those values of x less than negative 4. Next up, we have those values of x greater than negative 4 and less than 3. Then we have those values of x which will be greater than 3. And for what we have in the case of the tested value, for the input x, okay, so if I go with anything less than negative 4, we'll say we have negative 5. And we have anything between negative 4 and 3, but not including negative 4 or 3. Okay, we can go with 0. And then anything greater than 3, okay, we can go with, say, the number 4. Okay, so just looking at testing each of the inputs. Okay, so we have for r of x, if x is at negative 5, okay, now we're going to have r of negative 5 is equal to, and we've got negative 5 plus 4 over negative 5 minus 3. Negative 5 plus 4 is negative 1. Negative 5 minus 3 is negative 8. And a negative over a negative, okay, is going to be a positive. Okay, so for this output, okay, we're going to have a positive 1/8. For what we have in the case of r of 0, in case we have 0 plus 4, all over 0 minus 3, so we have 4 over negative 3. So this will yield negative 4/3. And for what we have in the case of r of 4, okay, just inputting 4 for x. Okay, so we have 4 plus 4. All over 4 minus 3. So you have 4 plus 4 is 8. 4 minus 3 is 1. You have a ratio of positive values, so the output here is going to be plus 8. And just taking what we have, okay, just again setting up the table. Okay. So separating into rows and columns. Okay, so for what we have in the case of the sign of r of x, here we go. Okay, so for any input selected that is less than -4, the output is positive. So we have the r of x is greater than 0. Anything selected between -4 and 3, 0 being the sample, output is going to be negative. So we have the r of x is less than 0. And then for any value x selected that is greater than 3, the output is going to be positive. So we're going to have that r of x is greater than 0. And just looking at sizing everything up, okay, in terms of how we're going to have the rational function to compare to 0. I think what I'll do here is just going to work to the side here. Okay, so yeah, first of all, okay, so if I have that x plus 4 over x minus 3 is less than 0, we're looking at where we had the r of x. Let me do this. Yeah. So we have r of x is less than 0. So where r of x is less than 0, okay, we've got between -4 and 3. Now we have x plus 4 over x minus 3 is less than or equal to 0. So we're looking at where r of x is less than or equal to 0, and this is where domain is going to be stressed. Okay, you're still looking at working around -4 and 3. Okay, now -4 is in the domain, 3 is not in the domain. And okay, so -4, any 0 that is in the domain, if you got the equal sign, you can put that around a bracket. But if the 0 is not in the domain, regardless of whether you have the equal sign, you're going to have a parenthesis around 0's not in the domain. So this will be how this is going to appear. Now for x plus 4 over x minus 3 is greater than 0. So r of x is greater than 0. So here you don't have to worry about what will be in the brackets, what will not, because of the lack of the equal sign. Okay, so we have two interval sections. So you have those values of x less than -4. And those values of x greater than 3. Let's see if I can duplicate this. Okay, now where we have that the function is greater than or equal to 0. We have r of x is greater than or equal to 0. And again, separating what's in the domain and what is not. Okay. Again, -4 is in the domain. We got the equal sign, the -4 in the domain. I can bracket this. 3 is not in the domain. Any 0 not in the domain, again, doesn't care whether you have the equal sign or not in the inequality, so that is going to stay in the parentheses. And so these will be your respective interval solutions for what we have among these comparison to 0 inequalities with the function x plus 4 all over x minus 3.